Everybody, welcome to class 108. So in this class, you're going to be using Coulomb's law. Just to find that on your reference table, that's Fe equals K Q1 Q2 over R squared. All right, we used it a little bit last time, but you're going to be using it a lot today, solving for all those different variables. All right. All right, and I put it up here just for our reference today. All right, so I put all the answers here to all the questions. Your job is going to be to show work for them, and all you're going to be doing today is uploading it, and I'm going to be checking the work for each of them. All right, we're going to go through a couple of them together, but we'll just talk about a few things throughout. So we're going to do numbers 5 and 7 together. Just a few things I want to point out first, though. First thing, make sure microcoulombs, remember, micro is times 10 to the negative 6th. So for example, this one would be like 2 times 10 to the negative 6th coulombs. All right. Centimeters, got to convert that. Centi is that's 7 times 10 to the negative 2 meters, or 0.07 meters. All right, so make sure you do that. Everything's got to be in standard units and before you even start. So let's look at number 5. So number 5 says 2 identical charges. So right there, that tells me that Q1 is equal to Q2. Are set 85 millimeters apart. So 85 millimeters, milli is times 10 to the negative 3. So our distance is 0.085 meters, right? If you look here, 1, 2, 3, yeah. Our electrostatic force is 75 newtons. And we're looking for Q. Remember, they both have the same charge, Q1 and Q2. So setting it up here, we have electrostatic force is equal to K, Q1, Q2 over R squared, 75, and I'm going to leave the units out for now just to keep it simple. K, remember, is 8.99 times 10 to the 9th. That's on your reference table on the first page. Since Q1 and Q2 are the same, I'm going to replace them with just Q squared. Okay, well, let me just show you where that comes from. So Q1 and Q2 are the same, so just be Q times Q. So Q times Q is just Q squared. Over 0.085. Don't forget to square it. Now, the hardest part of this is just the algebra, but you have to practice it. You have to be able to do this. First thing we're going to be able to do, or I'm going to do, is I'm going to cross multiply 75 times 0.085 squared, and I get 0.542 equals 8.99 times 10 to the 9th Q squared. Then I'm going to divide both sides by 8.99 times 10 to the 9th, and then take the square root. And when I do that, I'll get what the answer is here, 7.76 times 10 to the negative 6th coulombs. And you should just realize that coulombs, or excuse me, times 10 to the negative 6 is the same as micro. So I can replace the times 10 to the negative 6 with micro. All right. So again, you're showing work for all of these ones here. And we're also going to do 7 together. I like 7 because it ties in some force stuff that we did all the way back in the first quarter, while also, applying it to electrostatic force. So just read through the question quickly. The distance between each is 2 centimeters. So that's 0.02 meters. All right. Let's see. We're given the charge of each one. So sphere A is 1 times 10 to the negative 6th coulombs. Sphere B is positive 4 times 10 to the negative 6th coulombs. Sphere C is positive 2 times 10 to the negative 6th coulombs. Again, it's micro, so it's times 10 to the negative 6th. So the first thing you have to do is, and we're not even done reading the question, it says draw in the vectors to represent the force of A acting on B. So just look at A and B. Is A pushing B to the right or pulling B to the left? They're like charges, so it's going to be pushing it to the right. They're repelling each other. So I'm going to label this as the force of A on B. It says draw another vector to represent the force of C acting on B. So is C going to pull B to the right or push B to the left? Remember, they're both positives. They're like charges. So it's going to push it. They're going to repel each other. So force of C on B. So A's pushing it to the right, B's pushing it to the left. Now are A and B pushing on each other? Yeah, but just forget about that. We're just focusing on B right now. So the first one says, solve for the force of A acting on B. So we'll start with the FE equals K is 8.99 times 10 to the ninth. Q1 and Q2, well, in this case, Q1 is going to be 1 times 10 to the negative 6 coulombs. Q2 is going to be 4 times 10 to the negative 6 coulombs. Right, because that's A and that's B. So we have 1 times 10 to the negative 6, 4 times 10 to the negative 6, and the distance we said earlier is 0.02, and that's going to be squared. I'll leave the units out for now. If you throw that all in your calculator, hopefully you get 90, and let's just double check. Yeah, you get exactly 90. Just as a reminder, I use 9 times 10 to the ninth. I never actually use 8.99 in my calculator. So it's 90 newtons, and it looks like that force is pointing to the right. Now let's do the same thing here for the force of C acting on B. So we're just looking at those two spheres. So we have the electrostatic force equals K, doesn't change, 8.99 times 10 to the ninth. All right, so we'll call C will be Q1. So Q1 is 2 times 10 to the negative 6 coulombs. Q2 will be B. It doesn't matter which is which though. 4 times 10 to the negative 6 coulombs. It doesn't matter which is which because multiplication is, I don't remember what the word is, commutative. Whichever math property it is where you switch the order doesn't make a difference. All right, so we have 2 times 10 to the negative 6th. And we have 4 times 10 to the negative 6th. All over, and the distance here is also 0.02 meters. All right, throwing that in your calculator, you should get 180 newtons. You could tell it's going to be twice as big because the only difference between this one and this one is that one of the charges was doubled, right? If I'm doubling one of the charges, in this case, instead of being 1 times 10 to the negative 6th, I'm making this one 2 times 10 to the negative 6th. If I double one charge, I double the force. And that force is pointing to the left. So it says use your answers from A and B to solve for the net force acting on B. So F net equals 90 newtons, right? F net is the sum of all the forces acting on it, plus 180 newtons. So that's 270 newtons, should be our net force. Oh, why do I have 90 there? Oh yeah, it's because this force is pointing to the left, right? So since this force is pointing to the left, when I add it, I should make it negative, right? We make vectors to the left negative generally, vectors pointing down negative, vectors pointing to the right positive, vectors pointing up positive. So actually, I should change this to a plus negative 180 newtons. So I get negative 90 newtons. But what does the negative tell us? All that negative tells us, it's not that we have a lack of force, it's that we have 90 newtons to the left. So if I write 90 newtons to the left, I don't have to write the negative. The negative only tells me that it's pointing to the left. So 90 to the left is just fine. And we have a couple multiple choice questions here. Just give a brief explanation as to why the graph takes this shape. We spoke about it a couple classes ago. It has to do with the inverse relationship between force and distance. All right, so good luck with the other ones. If you have questions, pop into Extra Help Wednesday, basically, so tomorrow at 2:30. All right.